I want to go over a few of the points in chapter 13. So now what's happening is that a lot of the stuff that we have covered earlier in the course is now we're using it, and some stuff we see again. So here, the point here, we're spending a lot of time talking about the basis of air pollution, right? So we've already done our Earth chapter, which was chapter 12, and now we're moving on to air, and of course the next one will be water, okay? So when we're looking at here, so we're not going to spend quite a bit of time going over the different types of pollution, and hopefully you'll sort those out. But you can see that this is quite serious, and so 7 million deaths occur as a result of air pollution. So that's 1 in 8 deaths worldwide, and that was back in 2012, right? So it keeps getting worse. Now, in our part of the world, there are deaths that occur because of air pollution, but clearly not as many as in other parts of the world. So this sort of talks about the whole population. Okay, so let's get going with this. There we go. All right, so the first part, I'm just sort of laying out the basis of what we're discussing here, the different layers of the Earth's atmosphere. Just like when we talked about the Earth itself, there was layers, 3 layers, right? Crust, mantle, core. There are also layers based upon the different properties of the atmosphere as well. So the part that we live in is called the troposphere. So that's the one at the bottom. And here, as we understand it, as you go up in altitude, it gets colder, which is why at the top of the mountains there's snow, at least for now, because it's colder up there. And this is the part that has the gases that we breathe, and that's the point that's down here. Okay, so these components are here at sea level. So this is what you'd find in the troposphere. And as you can see, it's mostly nitrogen. Of course, we don't breathe nitrogen, so we'll go over how we get our nitrogen. Oxygen, which is obviously important. And in that, there's argon and CO2, as well as some trace gases. And if you're wondering what those are, you can see them here. There's all kinds of trace gases. And you can see some of them are involved in pollution later on. So it's not that these gases don't exist in the atmosphere, it's just that at the levels that they're going into the atmosphere is what is not normal. Okay, now above the troposphere is the stratosphere, and this is where planes fly. You can see that here. And this is also the place where we have our protective ozone layer. All right. Here, alternatively, as you go up in altitude, the temperature is actually going to increase because now you're getting exposed to radiation from the sun, and that's going to heat that up. Now, the mesosphere is above that. Okay, so you can see where we're dealing with. You're going to 50 to, I guess, 85 kilometers above the ground. And then above that is the thermosphere, all right? And now you're going up to the exosphere, which would be outer space. And here you can see where you have your auroras. They're up in the thermosphere, all right? Now, let's go over this. So nitrogen, right? So nitrogen is 78% of the gases in the atmosphere. And you can see in our layer in the troposphere, we have mostly nitrogen. Now, it is found as N2, that's nitrogen gas. And it is a very, very stable molecule. Remember, it has 3 bonds between the 2 nitrogens. But we need nitrogen, right? So nitrogen is found in DNA, RNA, and protein, as well as other things. So we need to get at that nitrogen. And so what is necessary then is that this nitrogen in the atmosphere must be fixed. Okay, what does that mean? That just means that they are going to be combined with another element, and in so doing, they become much more, the nitrogen becomes much more accessible to us. Now, here, in order to understand that, we can talk about the nitrogen cycle. So this is the process of taking nitrogen from the atmosphere, using it, and then sending it back again. So it's got to be a cycle. And the way we do this, in order to break those 3 bonds, some energy has to be put in. And the way that's done is by using the energy of the atmosphere. So lightning would do that. And this would start fixing that nitrogen. This would be combined with oxygen, which is what you're seeing here. So you can see that this nitrogen dioxide will then also be reactive, because now those bonds are broken. It can also then react with water, and then you get nitric acid. Okay, so now this is fixed and it will fall to the earth, and then we will be able to then get access to that. All right, so what ends up happening is that plants will start using those nitrates and nitrites. This is what they form here. So this would be your nitrate, right? And nitrite, I should say, and your nitrate is the NO3, and they're going to be incorporated into plants. And then, of course, we eat the plants, and therefore we are able to then use it. There are also plants that have bacteria in their roots, so legumes, for example. They're also able to take nitrogen from the atmosphere and convert it into a form that we can use. So they can fix nitrogen on their own. There's also an artificial way of doing this. It's not technically part of the natural nitrogen cycle, but we also can artificially fix nitrogen, making ammonia, right? So we'll take N2 and mix it with H2 gas and make ammonia. And this is sort of the basis of making fertilizers. So this would be industrial fixation, and this can then also be used. And this is what we use. So it's the Haber or the Bosch, Haber-Bosch process. Sometimes you just hear it called the Haber process. So that's what that means. So that's sort of the artificial way of fixing nitrogen. All right. Now, in the oceans, of course, there are also bacteria. So here we've got legume bacteria. But in the ocean, there are cyanobacteria that are also able to fix nitrogen and make that accessible to organisms living in the ocean. Okay. And how do they do that? Well, these bacteria will take the N2 and also make nitrates and nitrites, just like what we get from the process of using nitrogen, gas, lightning, and water. All right, and that's how that works, right? So the first step, making the nitrous oxide, and then making the nitrate. Sorry, I always get this mixed up. Nitrite, and then we get our nitrate. Okay, so ite is O2 and ate is O3. All right. Now, how does that go back again into the atmosphere? Well, decomposition. So when organic matter decomposes, there will be bacteria that can break down the nitrogen and send it back as N2. So these are denitrification bacteria that are able to do that. All right. Now, the other part is the oxygen cycle, and we sort of already kind of went over part of this, the main part of this, which is when we did redox, right? So we had the ability to take CO2 out of the atmosphere and produce oxygen, which is what plants do, and then the reverse. We use the oxygen and expel out the CO2. And that's a process of also making and using food, okay? Now, where does some of the O2 come from? Well, remember, we have the ozone layer. There's O3 up there. We've got all kinds of stuff going on in that stratosphere. And what can happen there is that energy from the sun is going to break down water, and it will then produce oxygen gas, O2, and then that can also be worked on to make ozone, O3, which up in the ozone layer is important, but down here on Earth, down here in the troposphere is what I should say, it's poisonous, all right? So oxygen molecules, you can say, react to form ozone, which is capable of absorbing UV, harmful UVB light. So here you can see the reaction. So with UV radiation, with up there with the UV, we're also going to break down. So you can see it's a double process. It goes both ways. We're also going to break down that ozone and then make oxygen again. right? So it's sort of a reversible process, something to think about, okay? Now, of course, in the troposphere, oxygen is going to be used during metabolism and combustion and decomposition, and that's producing carbon dioxide as a waste. Carbon dioxide, of course, is then going to be converted back into oxygen by photosynthesis, and we talked about that already in this course. So that would be our oxygen cycle. Now, I'm just looking at the notes to see if there's anything that I left out. No. Oh, yeah, the other thing, remember that for us, this is food, right? And plants produce that, and that's why we eat them, or we eat organisms that ate those. So that's is the whole process. And in my notes, I sort of broke it down to just O2 and CO2. So O2 using metabolism, decomposition, and combustion going to CO2, and CO2 via photosynthesis going back to O2, and that would be your oxygen cycle. And then we can get more oxygen, of course, from the stratosphere because of these reactions that are catalyzed by sunlight, okay? Now, the next idea is getting us into the chemistry of the atmosphere in terms of pollution. So what we just talked about, oxygen cycle and the nitrogen cycle, sort of the natural cycling there. But we have conditions because of temperature. This is why we brought up temperature. For us, usually as you go up in altitude down in the troposphere, things get colder. But there can be conditions in which warm air will sit over the colder air. And this causes problems called temperature inversion. And from all of our wastes that we produce, this can then be problematic because it will not allow wastes to go out into the atmosphere and be distributed, but instead they'll be trapped and they form smog, right? Now, there are several different ways that this happens. The two main ways, of course, are just weather, right? So you have an area of cold air forcing up warmer air at an advancing front, and that will put the warmer, lighter air above. Or topographically, you can have valleys and cities in the bottom of the valley, and they can have colder air trapped underneath here as warmer air comes in from other places, all right? And this is here an example of that. So this is nighttime temperatures above the valley cause a temperature inversion, all right? Okay, so I'm just looking through here, making sure I'm not missing anything. All right, so now, pollution. So what is a pollutant? Well, anything that is in the wrong place at the wrong time, that's a pollutant. Of course, we have many different ones that are problematic. But there have been, and this is something that I should mention, of course, that there are natural sources of pollution that cause problems, right? So that would be wildfires, dust storms, and volcanic eruptions. And as you probably know, if debris from space hits us, so like comet or something like that, and this is supposedly hypothesized one of the reasons that the dinosaurs went extinct, a comet or a meteorite hit the Earth, I guess it was a meteorite, and all of the debris then went into the atmosphere and cut off the sunlight and caused havoc, killing many species that could not adapt to that. But usually when we think of pollution, we think of things that are put there by us and causing these problems. But obviously from the wildfires that have happened in the past few years and the warnings that went out in those areas, because of climate change, the increasing amount of burning that we're getting is really, excuse me, just got a tickle, is also causing that kind of pollution, natural pollution. And you could argue why those wildfires are occurring, of course, but that is an issue. Excuse me. Other things, just cooking and heating fires, decaying waste, and then of course the advent of industry, of course, then really brought home pollution. And in my notes, you can see that there's already first laws back in the 13th century to help control this, because people realized that they were doing things that they could that were dangerous and putting stuff in the air that was harmful. Now, now when it comes to pollution, we kind of divide up the different types of smog. So industrial smog and photochemical smog. And there's a little bit of overlap, of course. But in general, I'm going to put just a couple of rules to kind of think about. So when it comes from industrial smog, obviously this is being produced by industrial activity. And here we have oxides of carbon and sulfur. That is not to say that non-industrial activity doesn't also produce carbon and carbon oxides and sulfur oxides, because they do. We just talked about cooking fires, right? Burning your fireplace, there's going to be oxides of carbon there, all right? But in terms of where does the bulk of this kind of smog come from, it comes from industry. So here you can see anything that's burning, obviously we're going to mix it with oxygen and we get these oxides of carbon. And we have carbon dioxide and carbon monoxide. Carbon monoxide is toxic, which is why people die of carbon monoxide poisoning. Oxides of sulfur, and this comes from a lot of places. When we talked about industry and smelting, sulfurs are going to exist. Back when we talked about copper, sulfur was one of the main things that combines with copper, but obviously it also comes out of other processes. And I think you might already know this, in the process of making iron, of course, and steel, we have to get rid of sulfur, and that is also a problem from that. So and then here, coal, where is it coming from? Well, because when we are making coke, right? So remember, coke is a very pure form of carbon that we need to make steel, and in making in purifying iron or from its ore, it has the burning of that coal contains sulfur, and we're making sulfur dioxide here, and this can then be further oxidized to sulfur trioxide, and then it can react with water in the atmosphere, and then we get sulfuric acid. So you can see that this is quite an issue. And in here, unburned carbon is up here, soot, all right? So that would be particulate matter as well, all right? Now, when we talk about this particulate matter, we're just burning that coal, we're making ash. Some is going to remain in the chamber, that's going to be bottom ash. Some is going to get out into the atmosphere, that's fly ash, and then you can inhale that, right? There are ideas of trying to mix fly ash or ash with concrete and trying to sequester that. And here's a picture of that. You can see that here. But we'll inhale it, and that's a problem. And you can see here, this is in the United States. Particulate matter, 40,000 premature deaths each year as a result of it. And obviously inhaling acid, sulfuric acid and those kinds of particles in the atmosphere will also affect our lung tissue. And environmentally, acid rain. I want to talk a little bit about that too, because it's not just coming from industrial smog, but also from urban smog. So our photochemical smog, the things that we produce on a daily basis, and it has nothing to do with industry. All right, so how do we try to get rid of that? Well, there's a few ways of doing that. So in industry, in the stacks, they have what we call electrostatic precipitators. Here, the charges on the particulates can be used to try and attach them to a charged plate and prevent them from going out into the atmosphere. Literally, bag filtration. So here they have filters that will try to filter out substances from that. Cyclone separators, this would be having the air move, and then in a cyclone, and heavier stuff will then come out or hit the walls and then be pulled out. Wet scrubbers, so actually passing water through and having them precipitate out that way before they get out into the air. The other thing is sulfur dioxide. It can be reduced, right, by removing the sulfur from the coal before it is combusted. And the way they do that is by adding limestone. And you can see the chemical reaction that's taking place here. They try to pull it out before they start burning it to make coke, for example. So there's different ways of doing that. So electrostatic precipitators, bag filtration, cyclones, wet scrubbers, I think those make sense. And then of course, trying to get rid of it before you send it, before you actually use it. And that would be the last step there, okay? So there are ways of trying to mitigate that, but obviously it still comes. Now, pollution, and this is going to be a big part of photochemical smog, which is the automobile emissions. This just comes from cars, and you probably know that. They're trying to get you to stop using your car, use public transport. I mentioned in class, I believe, that in certain cities, they'll only allow certain people with certain plates to come into the city on certain days. And so say if they end with an odd number, or they have an odd number in them and an even number, and that way they sort of distribute out the opportunities half and half and cut the traffic that way, and other things. So where does this come from? Well, obviously burning of fuel, right? So that fuel, we call it gasoline. It's a mixture of hydrocarbons. You know what they are now. Octane is what we say, it's sort of an average because it has 8, but anyways, the carbons go from 8 to 12. But remember, you're burning. So you're making CO2, which of course we know is a greenhouse gas. But they also don't burn that fuel completely. So that would be carbon monoxide that's going to come out. And obviously that is toxic. And these things, both of them are greenhouse gases. So they also warm the earth as well, which we'll talk about in a bit. All right. So here you can see how oxygen and CO, carbon monoxide, binds to hemoglobin. That's what this is here. This idea here. You have iron in your hemoglobin, and actually carbon monoxide has a better affinity for your hemoglobin than does oxygen gas. And that's why it is so toxic to us, because it will displace oxygen and you die of asphyxiation. Now, nitrogen oxides. So the other thing that happens in engines, not just the burning, but the heat there, that is also going to, and you think about it, fixing nitrogen, but it's also going to encourage nitrogen to mix with oxygen. This is very similar to what we were looking at in terms of our lightning, right? And you're making your nitrates, right? And they, of course, will then mix with water, and you make your nitrates and your nitric acid, and this is a problem. All right, so here we call them NOx's because they cover the whole gauntlet of NO, NO2, NO3. And then, of course, there are other things that don't get burned at all. So those would be your volatile organic compounds. And as you know, you can smell gasoline at the pump. You know that it's volatile. At this point, you know it's not an ester, but it is volatile. So it goes into the air, and you can smell it. You've got chemoreceptors in your nose that can smell that. But also remember back when we talked about organics, right? A lot of organics are also volatile, or the elastizers and that kind of thing that we put in there to make those hydrocarbons or those organic polycarbonate polymers last longer, right? These are also toxic and go into the atmosphere, okay? Now, so what are we dealing with? So we have industrial smog and photochemical smog. So now let's add a name to that automobile emission smog. But it's not just automobile, automobiles clearly are our main source, right? But there's also our organics. There's also going to be some ozone that's produced as well in those engines, right? So remember our cycle that takes place in the stratosphere. We can convert oxygen to ozone, and ozone back to oxygen because of the heat from the sun and UV radiation. But this can also happen in engines, all right? So here we have our hydrocarbons and our NOx's, and here are on the other side our industrial smog, primarily carbon and sulfur oxides. And here they're stressing this. Very often these are very different names, right? London smog, right? So here we have cold, damp, foggy weather, and over here when we're dealing with photochemical, you're adding in that heat and that temperature inversion, and we have photochemical, and that has that sort of yellowy haze to it, all right? Now, So photochemical smog. So everything sunlight is now going to react with all of that smog that we have. And what they're trying to do. So one way to mitigate this, of course, was to add catalytic converters to cars, makes them more efficient burning. Okay, and that, of course, will help trying to reduce the emission of volatile organics. Um, but we also have these other things, right? So we have ozone, aldehydes, many other things that are being produced here, and we haven't done a lot to mitigate these things, okay? Now, acid rain. So what happens because of these? Well, one of the effects is acid rain, and sulfur and nitrogen oxides acidify the air because you're getting nitric acid and sulfuric acid. And this is very destructive. It causes corrosion, breaking down of concrete. And remember, concrete, when we talked about earth, concrete is one of our main building materials along with steel, right? And this will be broken down by this pH. So this is affecting us as a civilization, but also the environment is changing the pH of rivers and lakes. It kills plants and trees. It's very, very destructive. And that's sort of what I'm showing you here. So again, remember, these are coming from industrial and automobile emissions. They oxidize, combine with water, and fall as acid rain. Now, if you thought you were safe inside, here's a list of your internal or inside sources. So carbon and nitrogen oxides, your stove, cigarette smoke, kerosene heaters, mold. We never talked about that yet, but mold in the house can be very damaging to you in terms of your health. Ozone, it actually comes out of coffee machines, air cleaners, all kinds of stuff like that. You can actually get ozonators. Supposed to help, but I don't really know how that's a good thing. But you can get those cigarettes, secondhand smoke. We talked about radon before when we did radioactivity, or chapter 11. Colorless, odorless, tasteless, but very high percentage to the point where it could be dangerous in rock here in central New York. And this can break down into polonium-218. Again, still emitting radiation, off gases, so from our organics, of course. Now, ozone, we mentioned it already. Of course, we need it in the troposphere. I mean, in the stratosphere. In the troposphere, however, it's hazardous. It's toxic, and contributes to smog and air pollution. Right? In the stratosphere, it's necessary. And how does that happen? Well, in the mesosphere, remember, the light is going to come through the mesosphere. Radiation is going to help split those oxygen atoms. We already went over this, how this happens. All right, so some of that reactive oxygen is going to interact with oxygen gas, and you're going to get ozone. All right, now don't forget, when we talked about our organics, our chlorofluorocarbons, or CFCs, they are reactive with ozone, and they break down ozone. They produce oxygen, but they reduce the amount of ozone, and that is dangerous. And where did these come from? Well, refrigerants and propellants and that sort of thing. So there was a global reduction on this, and it's still being worked on. The link here talks about the Montreal Protocol and the Vienna Convention, looking at how to save the Earth from this. And this has been very successful. So if only we could do that now. But that would be talking about climate change and many of these particulates. Now remember, they do occur naturally because of things that happen on the Earth, but our activities greatly increase the amounts of these greenhouse gases, and that is contributing to what we call global warming. But it's probably a better way to think about it as climate change. Because different parts of the world are going to see different effects of this. But overall, when they're talking about global warming, they're not talking about you right here and around here at school. They're talking about a global change in this, average temperatures. All right. So now these greenhouse gases, we do need them to a certain degree because they help keep us warm. Sunlight comes through the atmosphere, interacts with materials on the Earth, and It's these reactions then give off heat, and it is these greenhouse gases that help hold that heat in. Otherwise, they'd all get lost to space, that heat, and we wouldn't be able to live here on the planet. But too much of a good thing is a bad thing. And this is where this idea comes from, all right? Now, you can see that, and yes, there has been changes, of course, right? A meteor hits the Earth and puts all these particulates into the atmosphere. There's going to be a change, right? But the change that we are producing has never been on a scale that in the history of the Earth, and we're doing it so quickly that it's almost impossible for organisms, including us, to adapt to these changes. And the tremendous amounts, and we mostly focus on CO2, but that is not the only gas that, or the only greenhouse gas, right? But that's the one that is increasing the most. Methane is the other one, and that is largely because of our activities, or as a consequence of our activities, all right? So what is going to be a problem? Well, you know this, right? Impacts on food production, flooding, infectious disease with all kinds of strange differences in the climate. Extinctions are happening because the animals can't adapt quickly enough. And extreme weather, I haven't even listed that here, but that's another one. And in general, the models have actually underestimated the effect that is taking place here. So in my notes, I list economic damage, health damage, sea level rise, loss of habitat, decreased biodiversity, and ocean acidification. All of these things are happening. Now, what are our greenhouse gases? And I list them in my notes. So we're dealing with CO2, obviously, but other greenhouse gases, water, of course, methane, as I mentioned, CO and chlorofluorocarbons, CFCs, all of these have a role to play. So what do we do? What do we do about this? Well, the main way is to try and decrease our carbon output. And in order to do that, we need alternative energy sources or renewable energy, all right? More energy efficient cars and appliances. Carbon capture, this is one that you probably heard about in the news, and how to do that and how to charge for it, and then using that money to try and develop alternative energy sources. So there's a lot of debate on this, but you know, it comes to the point where how long do we debate? We need to do stuff. Now, in terms of pollutants, there are the top 6, the EPA critical 6, carbon monoxide, all right, nitrogen dioxide, ozone, particulates, sulfur dioxide, and lead, right? We haven't even talked about metals going in the atmosphere, but this is a big one, lead, okay? And we'll talk more about that. Now, out of these 6, all right, hydrocarbons, in addition, have serious effects, all right? I didn't even list that. Now, what is causing the pollution? Who's polluting? Well, here you can see motor vehicles are a big one, power plants, smelting, industry, and then here we have a little bit from natural sources, but these are being thrown askew as well because of climate change. So you can see it's all of the, and then here it summarizes the health effects and environmental effects. So you can get a better readout on exactly what's happening. And that is chapter 13. So hopefully that review has helped a bit, and I'll make another video for the next chapter.